start recording this time. So let's share our screen, and here's our, okay. So let's open up a new sheet. Now before diving into this example, I want to very briefly talk about what I call generalization of system models. Now we mostly, in 302, we mostly dealt with, sorry, let me also turn on my video. We mostly dealt with electrical, mechanical, and electromechanical systems. But in this course, we will also look at fluidic systems, thermal systems, other physical variables. So it is helpful to remember that many system models share common principles. One of these is that we have components often, okay? Components. Now, each component often basically have a true variable going through it. We call this the true variable. You can immediately identify the electrical analogs, right? The true variable in electrical circuits obviously is the current, okay? So for example, the current in electrical circuits. Also, every component will have basically an across variable, okay? Let's call this the across variable. Obviously, in electrical circuits, this is our voltage difference. Okay? Now, let me generalize this. There are other obvious examples. For example, in fluidic systems, the true variable obviously is the fluidic flow, something flowing through components, and the across variable is the pressure difference. Okay? So there are less kind of obvious examples as well. Let me put these systems. In general, we can have electrical systems, we can have translational mechanical systems, mechanical. These we have seen in 302. We can have rotational mechanical systems. Now, all of these, right, were covered in EE407. But now in this course, we will also look at fluidic systems, and also thermal systems as well. There can be chemical systems as well, but we're not going to go into chemical systems at all. Okay, so this is more like EE402 edition. Sorry, not 402, 407. Okay. And let's also define these two concepts that we have, the two types of variables. We can have a true variable and we can have an across variable, right? In the electrical systems, we have the current indicated by I, and we have the voltage difference indicated by V. Now, when you go to translational mechanical systems, it becomes more interesting. The true variable is considered to be the force, okay, F. And the across variable is considered to be velocity difference. Linear velocity difference, okay? Let's call this, let's say V21. Obviously, this V is not to be confused with the voltage V, okay? And in fact, although we haven't done this, at least I don't remember, but every component in translational mechanical systems, their terminal relationships can be derived from between these two variables, the across variable and the true variable. In the rotational mechanical systems, we have torque rather than force, and we have angular velocity difference, this time omega 21 as the across variable. And when we come to our case, let me use a different color. Okay, now when we talk about fluidic systems, we have volumetric flow rate, often indicated by Q. Okay, in this case, this is meter cube per second. Okay, and you can write the units for these as well. Okay, and we have pressure difference. P21 unit is Newton per meter square. So force per unit area is the unit of the pressure. In the case of thermal systems, we have heat flow rate. Again, often indicated by Q. What was the unit? I don't remember. Okay, you will check that out. And we have, again, this time we have temperature difference. As our variable, tau 21 unit is degree centigrade. Okay, so this is the generalization of components in terms of different types of physical systems. Okay, for example, every thermal component has to be defined in terms of a relationship between the heat flow rate and the temperature difference. Each fluidic component, like a valve, has to be defined in terms of a relationship between volumetric flow rate and the pressure difference. This relationship may be algebraic, like in the case of a resistance, right, in circuit theory, or it can be differential, like we have done, like a tank. Okay, a tank is an energy storage device, like a capacitor in an electrical circuit. So we have a differential relationship that defines this component. Okay. Now let me very quickly introduce our example, and then we will finish for today. This example we will cover the next time. Okay. So example. This is a heat transfer process. Which is essentially a heat exchanger. This is from Fikar's book. Okay, so you can check that out over there. Now, the heat exchanger and the heat transfer process is actually everywhere. From your home heating devices to how our campus is heated, to laptop computers where the CPU needs to be cooled down. So, in fact, it's not only limited to industrial environments. It's also in many modern electronic devices. So it's really useful for us to have an idea about how this works. So let me sketch the diagram of this system. So what's happening is that we basically we are trying to see what's happening again with the liquid's this time temperature in a tank. So instead of the level, we are now interested in the temperature. So there is liquid inside. Okay. And we are mixing this liquid. So this is kind of a propeller, okay, mixer. The dynamics of this mixer is not important. The only thing to know is that the liquid is well mixed so that its temperature is homogeneous. Okay, so homogeneous temperature of liquid. Okay, that's all it serves. We have a heater. So you know, in this example, this is a valve. So we have basically a pipe going through. Okay. So steam coming in. We will simplify the process. We will not really dive into too much into what's happening with the steam and so on. But the heater, so this is our heater. It's basically transferring heat energy, thermal energy into the liquid. So there is liquid coming in with a certain input temperature, T in, and a flow rate Q. Okay, so let's try to write down our variables. So this is the temperature of inflow liquid, in degrees C. So we have volumetric inflow rate, volumetric inflow rate. So this is in meter cube per second. We have the volume of the liquid, V. So volume of liquid clearly is meter cube. We need to have the density of the liquid because we have to use it. Density of liquid. This is kilogram per meter cube. We have the specific heat, Cp. Specific heat. Specific heat is about how much this liquid is able to store heat energy. Okay, so how much heat is stored will be related with the volume of the liquid, its density, which will determine how much material is in this volume, and also the specific heat, which determines how this particular material, this particular liquid, can actually store heat energy. Okay, specific heat, I believe it's joule per kilogram. So it is related with the mass. Okay. Now, also, let's also define the heater. So the heater will have a temperature, heater temperature. It will have a contact area with the liquid, which will determine how heat is transferred, area of contact with liquid. Obviously, the larger the area, the more energy will be transferred to the liquid. And also the nature of the contact, okay? How is this interface? The material of the interface determines the heat transfer coefficient. Heat transfer coefficient. It's like a resistance between the heater and the liquid. Now let's define our aim and conclude for today. What is our aim? Obviously we are trying to model this system. Oh, sorry, by the way, let's also indicate here, we also have volumetric. So we have the temperature of the liquid coming out, okay, here. And also we have the outflow rate. Mind you that the inflow rate and the outflow rate in this case are the same. The reason being, if they were different, then the level would not be constant. Okay. Here we assume that the liquid level is constant, and we are really interested in the thermal behavior, the temperature behavior of this system. Okay. So the aim, so the heat exchanger, aim of the heat exchanger is often to regulate the temperature, to regulate the temperature of the outflowing liquid. Our aim, obtain a model of the thermal behavior of the system. And we will see that this will be a lumped parameter model. So all the models that I have discussed, thermal, fluidic, circuit theory, electrical, mechanical, these are all lumped parameter models. That means you have components, you have terminals of the components. Each component is defined by its terminal equations. And when you interconnect the components, you get topological equations. And you don't have anything happening distributed inside the system. We will later on have examples of distributed systems and how they work. But this model, this particular model that we will discuss, will also be a lumped parameter model. Okay. Peki arkadaşlar, bugünlük bu kadar. Sorusu olan varsa sorabilir. Çıkmak isteyen çıkabilir.
İyi günler hocam.
Görüşmek üzere arkadaşlar.